Hi, Honors Algebra. This is the beginning of Chapter 3. This is 3.1, and we're talking about linear equations as well as linear functions. For our objectives here today, we're going to be graphing linear equations by using the point plotting method as well as using our x and y intercepts. And we'll be showing you how to graph vertical and horizontal lines as well as applying linear functions to real-life situations. So, as always, anytime we have a review or warm-up, we want you to go ahead and pause it, try it yourself, and then come right back and join us, and we'll go over how to do that. So, if you came back and you already solved it, there's multiple ways to solve this problem for x. Some of you may have decided I'm going to subtract 4, multiply by 3, and divide by 2, or multiply by 3 halves afterwards. Totally up to you. I'm going to do this and approach this a different way, which is I'm going to multiply each side of the equation by 3. So this way our denominator will cancel out. So remember that you have to apply this 3 to each and every term on the left side. So even though it cross cancels with 3, you will get 2x plus 12 equals 0. And isolating that x value, x term, we're going to subtract 12 from each side, and we're going to get 2x equals negative 12, divide by 2, x equals negative 6. Simple enough. All right, go ahead again and let's try on your own to plot this equation. When you come back to join us, hopefully you realize that if we're going to plot by using a point plotting method, we want to put this in slope and intercept form first. Y equals mx plus b is probably the easiest way to do this first. So if I solve for y, I'm going to go ahead and subtract 3x from both sides. Notice that I kind of put it on the side there to show you that they are unlike terms. So when I divide by negative 2, I'm going to divide each and every term by negative 2. And of course, I'm going to simplify that. A negative divided by a negative is a positive 3 halves x minus 3. All right, so here is our equation. And from here, sorry, my funky looking 3. All right, I'm going to plot some points. So I could go ahead and make an x and a y column. And I'm just going to pick some random points, but I always like to pick 0 for x. So if I substitute in 0 for x, that means 0 times anything is always 0, minus 3 is negative 3 for y. Since this is a linear equation, and we could tell that by the exponent of the x and y, which is to the first power, we know that it would be nice to have good integers on our graph. So we want to make sure that we pick some value for x, like we taught you in 2.1. That would work nicely with this fraction. Since our denominator is 2, any multiple of 2 will give us a nice integer. So even if I pick 2 for my value, if I pick 2 in place of x, that would cross cancel here, and I'm going to get 3 minus 3, which is 0. All right, so if I picked negative 2 for x, I'm going to get negative 1 because negative 2 divided by 2 is negative 1, times 3 is negative 3, and negative 3 minus 3 is negative 6. So I have 3 solid points here, and now from this point, all I need to do is plot, and you get to choose any of those points. So those are just random ones I've chosen. You didn't have to choose that. So if I go ahead and I plot 0, negative 3, it's right there, negative 2, negative 6, which is right here, and 2, 0, which is right there. So if I go ahead from this point and I draw my line, and again, make sure that you put arrowheads on both directions, all right? So there's our line. That's what your line should look like. Doesn't have to be that big for mine, but there you go. So our next example is graphing each linear equation by plotting points. So again, you can go ahead and solve for y. That seems to be the easiest thing. And normally you're thinking probably, maybe you're thinking, what if I did that by just covering up and finding my x and y intercepts? You can do that eventually, but for this method, they want you to plot points, and you'll see in the next couple examples that we're going to use our intercepts for that. So right now, I'm going to go ahead and solve for y. So I have negative y equals negative x plus 4. And all we have to do here is divide by negative 1 to each term, or when you divide by negative 1, it switches the sign of all of those terms. So we have y equals x minus 4. So if I go ahead again and make a table of x and y values, I can go ahead and substitute in whatever points I want. You know, depending on what teacher you have, it could be 2 points or 3 points or whatever you want, but I'm going to go ahead and pick 0 for x, so I know that I'm going to get negative 4. I'm going to pick negative 1 for x, so negative 1 minus 4 is negative 5. And I'm going to pick positive 1 for x. So 1 minus 4 is negative 3. So here we actually have a graph that goes with this picture, with this equation. So I'm going to plot negative 1 comma negative 5, 0 comma negative 4, and 1 comma negative 3. And again, just draw your line, making sure you pass through all the points, and you put your arrowheads in all the directions. Okay. And that's it. And now if you can't see those points again, just make them just a little darker. There we go. All right. Next, kind of covered up my equation here with the last line I drew. So I'm going to make that invisible by deleting that line, and we have our new equation here. So again, if we're going to use the plotting point method, I'm going to get rid of this fraction first. So I could actually multiply each side by 2. And remember, that means you're multiplying each term by 2 on the left side, which gives us negative 6x minus 1y equals 2. So again, if I put this in slope-intercept form first, by adding 6x to both sides, I'm going to be left with negative y equals positive 6x plus 2. Dividing everything by negative 1 to each and every term would give us y equals negative 6x minus 2. So using that equation, I'm going to go ahead and make a table of values for my x and y's. They want us to plot some points. So again, if I were to substitute 0 in for x, I'm going to get negative 2 for y. If I substitute in negative 1 for x, well, negative 1 times negative 6 is positive 6, and 6 minus 2 is 4. If I substitute in 1 for x, positive 1, I'm going to get negative 6 minus 2, which is negative 8. So I'm going to go ahead and plot those 3 ordered pairs. So negative 1 comma 4, 0 comma negative 2, and 1 comma negative 8. So making sure these are big enough so when I draw my line through them, you'll be able to see that. All right. So again, trying to make sure that your line goes through all of those points, whether you had 2 or 3 or 4 points. There you go. And we have arrowheads both directions. So that's how you graph linear equations, by plotting points. In our next topic, we're going to be graphing the linear equations by finding the intercepts. Remember, the intercepts are the place where the graph crosses and hits the x and y axis. So it's intersecting the x or intersecting the y axis. So that means if we actually make a little table here for our x values, let's do that again. For our x values and y values, now if we think about this, we've covered this before. When we're looking for the x-intercept, we're looking for the place where our graph crosses the x-axis. And if we're on the x-axis, our y value has to be 0. So that means our x-intercept is going to be some x value, comma 0. So I'm just going to write here that this is our x-intercept. And on the reverse of that, if we're looking for our y-intercept, we know that we're going to be on the y-axis, our x value would have to be 0. So that means we're just basically going to plot 2 points. We just have to figure out where that x and y value are. So if I look for my x-intercept, that means my y value is 0. If y is 0, I'm just going to cover that up because I know 0 times anything is 0. So really what I'm left with is just 5x equals negative 15. And if 5x equals negative 15, at this point I could just go ahead and solve for x, divide both sides by 5, x equals negative 3. So my x-intercept is at negative 3, comma 0. All right, and again for my y-intercept, I know that my x value has to be 0. So 0 times anything is 0. So I'm going to cover up. I like to call this the cover up method. If we cover this up, we're left with the equation 3y equals negative 15. So if we go ahead and solve for y by dividing everything by 3 here, y is going to equal negative 5. So that means I have my 2 ordered pairs where my intercepts are, which is 0, negative 5, and x-intercept is negative 3, 0. So all I have to do now is come on the graph and plot those points. Here's my x-intercept. Here, 0, comma negative 5 is my y-intercept. From this point on, I'm just going to draw a solid line through them. And again, as always, I know I'm a stickler for this. I'm sure all the other teachers are as well. But you definitely want to make sure that you put arrowheads signifying that they're going in forever in all directions. All right, let's look at B. So with B, this looks very messy. We have fractions. So instead of worrying about, oh my God, do I have to multiply by 3 or multiply by 2, if we can totally get rid of the fractions by multiplying by the least common denominator, LCD, the whole entire equation. So of the entire equation, the LCD is 6. So if I multiply both sides by 6, got to be careful again because you're going to cross reduce here. Doesn't technically all cancel out, but I am left with a 2 on top, and 2 times 2x is 4x. I'm going to write that up top there. And then this reduces to 3, so 3 times negative 1y is negative 3y equals 12. So from this point, we're going to go ahead and use the cover-up method. I know, again, if I make a chart of my x and y's, my x-intercept is going to be when y equals 0, and my y-intercept is going to be when x equals 0. So to find our x-intercept, if I cover up that y value, because I'm inserting 0 there, that means I'm left with 4x equals 12. And if we solve for x, divide by 4, x equals 3. There's our x-intercept. For our y-intercept, I'm going to cover up x because x is 0, and I'm left with negative 3y equals 12. And if I divide by negative 3, y equals negative 4. And there's my x and y-intercept. So all I'm going to do right now is plot them both. So 3 comma 0 is my x-intercept, and my y-intercept is at 0, negative 4. Again, making sure your line goes through those points in a nice, solid way, arrowheads in both directions. Okay? All right. Now, our next topic, and we're going to still carry forward, we're still graphing linear equations, but you may have noticed that the equation looks a little different. This doesn't look like slope-intercept form, and neither does B. But this is telling us that it's a line, and it says that our y value is 3. So whenever you get a problem like this, after some practice you may realize, oh, I know what that line looks like. It's going to actually end up being a horizontal line. But first, let's talk about how it ends up being that way. If our y value is 3, that means I can pick any set of points where the y value is always going to be 3. So if you just pick random points, let's make sure they fit on the graph though. So let's say I want my x value to be -4. I have to pick then my y value of 3 because here the equation is saying your y value is 3. All right? Let's say you want to pick -1 for x. Again, that y value associated with that -1 is +3. So basically you can randomly pick some ordered pairs here, but your y value in all cases will have to be 3. Okay, so you can go ahead and plot these. So -4, 3, -1, 3, 3, 3. And if you connect those points, you will see that you will end up with a horizontal line. And that horizontal line is at the equation y equals 3. What this is saying again is if you look at any, and again, from -infinity to +infinity, no matter what x value you chose, your y value every single time is 3. So anytime you have an equation in the form y equals a number, that's going to end up being a horizontal line. Okay? So y equals 3 in this case was our number. All right, so that's basically what your horizontal line looks like. So the equation of any horizontal line again is y equals whatever number you have. Let's look at this. What do you think this line is going to look like? Now we have x equals -2. Again, if you're trying to figure out, well, how do I draw that? That's telling us pick a set of ordered pairs, but our x value every single time has to be -2. So you can fill this in with anything you want. Just again, let's pick a y value that fits on our graph. So you could pick -7, you could pick 0, you can pick 6, whatever you want. But again, since our x value is -2, we want to make sure we're consistent. So if we go ahead and plot those points, -2, -7, -2, 0, -2, +6. There we go. We're done? Almost. We have to draw our line, okay? Going through all of those points. So, making sure that you put arrowheads in both directions. That's what our line's going to look like. Kind of moved over a little. All right. So that's it for almost forgot. So we have what's called a vertical line here. This is a vertical line, which is in the form x equals some number. Okay, and that's the equation of any vertical line. All right, let's talk about the perimeter of a rectangle. Now we're actually going to be applying linear functions here. So in a given rectangle, the length is 3 feet less than twice the width. If x represents the width of the rectangle, the perimeter can be calculated by the function p of x equals 2x plus 2 times the quantity, 2x minus 3. So normally I would say go ahead and draw your rectangle, and if you want, you can label it all you want. But what we have involved in this rectangle is the width and the length. So our width, we were told, is represented by x. Our length then is represented by 2x minus 3. Okay. And those are the expressions that each of them stand for. So they're asking us, what is the implied domain of the function? Now, we've talked about domain, set of all x values that works into our function. But the implied domain, since we're dealing with a real life situation, we have to think about it. If we have a rectangle, I'm going to draw this here. If I have a rectangle whose length is 2x minus 3 and the width is x, I know that in order for a rectangle to exist, I have to have some width and some length. My width can't be negative, my length can't be negative. My width or length cannot be 0, because if it's 0, we're not going to have a rectangle. So the implied domain of the function, so if we had to define that, it's the x values that make sense in this problem. So you're normally seeing, hey, well, this is a linear function, because if I were to go ahead and evaluate this, if I were to simplify this, I should say, I'm going to be left with 2x plus 4x minus 6. So if I take this a step further and simplify it more, I'm going to be left with p of x equals 6x minus 6. So basically all I did is I took our function, p, and I simplified it to something more condensed. And they mean the same thing, it's just that I simplified it. And if you look, this is in a linear function form. So it's going to be a line if we had to graph it. And you're thinking, oh, the domain's going to be all real numbers because it's a line. However, in our problem, we're saying that that represents the perimeter of this rectangle. So saying all real numbers is not going to work because I cannot have a width of 0. Putting 0 in here for x, I won't have a rectangle. Putting something in negative for x will not give us a rectangle because length and width, distance can never be negative. So the implied domain, we have to make sure